everyone, and thank you for joining my session. My name is Yonatan Goldschmidt, and today we're going to talk about into the flamegraph, about profiling, understanding profiling, and optimizing based upon them. A bit about me. I have 6 years of experience, mostly from the Israeli Defense Forces. I'm from Israel. I like everything about computers and software. I like wine. This is a photo of me from a wine trip in Italy, actually. I'm more into Italian wine now, but that might change. I'm also French, but my father didn't teach me his mother's tongue, so I'm giving a presentation on the English track and not the French track. And today, I'm a team lead at Granulate's Performance Research Department. Granulate, which, by the way, has signed the deal to be acquired by Intel a few weeks ago, enables companies to optimize their workloads, improve performance, and leverage that to reduce costs. To do that, we have developed multiple internal tools to profile and to optimize, and we gained a lot of expertise, and that's what we are going to talk about today. But first, we'll start from the back. Profiling is done for something, and the cause is to optimize. There are many reasons to optimize. The main two ones, the most impactful ones, are to reduce infrastructure costs, which are very high, as I'm sure most of you know, and to improve the SLA of our applications, so our users get better user experience. And where does profiling join in? I'm sure most of you have seen this sentence. We humans are not very good at reading code or inspecting an application and knowing which parts of it are the performance bottlenecks. We're not good at it. If we optimize without profiling before, if we optimize prematurely, we're most likely taking the wrong choices. We need to profile. So profiling. Profiling has existed for long times. There are many types of profilers. There are many types of tools. It's mostly used for optimization, but also used for debugging. For example, because I'm very acquainted with those tools, I use profilers as debuggers as well. Now, this is just a quarter of the page, the first page in Wikipedia about profiling tools. My point is that there are many tools. But still, we feel that profiling is not common enough. If I were to ask you now, who's ever used a profiler at any time in his life? Please raise your hand. All right. See it, many of you. Well, that's the type of audience for this talk. But who's used profilers in production, not on their box, developer box? Production, yeah. Fewer hands. OK, I hope that after this talk, the number of hands in the air will be higher. OK, today's focus will be CPU profiling. I focus on that because it's the simplest one to understand, and in my opinion, the most impactful one. CPU profiling refers to CPU time of executed programs. Here I have a simple Python line, 2 Python statements, a slip, and a sum of numbers. Both those statements take roughly 1 second on my machine. Summing up 100 million numbers takes about 1 second of computation, and slipping for 1 second takes, well, 1 second. But one uses the CPU, and another one does not. One will be profiled by CPU profilers, and the other will not be. Now, what exactly do we profile? Well, we can trace all functions being executed by our application the entire time, but that would induce a very heavy performance toll. Instead, we'll be sampling. What does it mean? We occasionally stop the program, and we inspect which functions are currently executing. We take a call stack of the currently executing functions of each profiled program, and over enough time, those samples will display an accurate image of which call stacks, which flows are common in our application. And then we know that those are the CPU-intensive one, and we can focus them. Now, as I said, CPU profiling is very easy to apply compared to other profiling types, and can have drastic implications on the performance of your application, from the conclusions that you can draw from it. So it's a good thing to start with if you've never tried profiling before. Now, before diving into profiling data, we'll talk about continuous and production profiling. Previously, we saw that not most of you have tried profiling in production, and we'll see now why it's important. Just like we humans are not very good at looking at code and understanding which parts of it are like more heavy or perform worse, we're also not very good at predicting which load our production gets. When I write code, I think of 1, 2, 3, 4, 5 cases. I test my code with those cases, and those cases usually end up reaching my load generator or my load tests. But my production usually sees other behavior, other inputs and patterns. Therefore, if I optimize the code based on my test cases, then great, my load tests will perform better, but not my production, most likely. So while profilers do work on my machine, you don't do that in real life. Another concept is doing it continuously. The first reason is that load is varying. Here I have somewhat modeled the load on a local food delivery service in Israel. I don't know about the food scene in Paris, but in Israel, when 12 p.m. comes, you order your vitrina, you try to order it, which is the best burger in Tel Aviv and probably in the world. I know many people try to order it, and they refresh the page continuously until the venue gets opened, so the load goes high. And then the load comes down a bit, and at dinner time, people again try to order dinner, and at night, they order their night cookie at 3 a.m. If I were to profile at, say, 10 p.m., the load will be very different from the load at 12 p.m. because the usage pattern is different. Users are using my application very differently, so the load is different. We have to profile continuously to see what's actually happening throughout the day and where my application peaks, for example. Another reason is that code often changes. We strive to have CI/CD and to be able to deploy multiple times per day, right? If I take a profile, let's say, one day and continue to work with that for days ahead, my code has changed meanwhile, and I'm working on stale data. We need to profile continuously. OK, now we'll start getting into profiling data itself. The focus of this talk is flame graphs, which are a way to visualize stack traces. Put simply, we have collected samples that are call stacks of profiled applications, and the flame graph displays them on the y-axis, displays a call stack. So here, if we have another bigger one, we have here MySQL index prev, and it calls into general fetch, and it calls into row search MySQL. It's just call stacks swapped. Now, the x-axis of a flame graph represents the relative number of samples that a function or a call stack had compared to other parts of the profile. Note that this is not how many times a function was called, because we don't know that. We are sampling, we are not tracing. A function could have been called 1,000,000 times and could have been called 1 time. We don't know. Also, it has nothing to do with passage of time. Names are ordered alphabetically. It has nothing to do with time. I put little links that you can read about flame graphs later if you want to. Let's see now a simple code example that will, I hope, will help your intuition understand it better. We have 3 simple Python functions, one that sums 1,000 numbers, another that sums 10,000 numbers, and another that sleeps for 1 second. If I were to ask you which one takes the most time, you'd say that the last one, because the first 2 are very fast. It takes a fraction of a second to run those on any modern computer. If we look at the profile, we can see that the sum 10,000 takes roughly 10 times the space on the x-axis compared to the sum 1,000, which makes sense because summing numbers scales linearly. So a function that sums 10 times more numbers will take 10 times more space on the profile. The sleeper function is not displayed here at all because it takes no CPU time, so we're not profiling it, despite it taking the most wall time in human sense. All right. So I've got a few samples of more advanced concepts that we'll now go over. I display them with our gprofiler, which is a system-wide open source. continuous profiler for production that we're developing, and it has a cool UI, but I'm biased. None of these concepts are were truly invented here. Everything here is from the open, and you can find other tools that let you view the data and do similar manipulations with it. All right, let's start with an example about mixed stacks. I have this simple Python code. It runs and spawns a process that exits immediately and sleeps for 1 second. When we profile a Python application, we often want to see the Python profile of it, like the Python functions, like we saw before, with some 1,000, some 10,000 functions. However, there's other code running in our process. For example, we do system calls, and they get into the kernel and execute kernel code. Or we call into libraries that are written in other languages, such as C++ or Rust or Go, and they're not Python. And oftentimes, viewing the call stacks or the parts that are not Python or not Java or not the languages that are profiled are overlooked. And we'll see now why that might be a problem. Let's add a simple change to this sample. Just creating some list with many, many numbers. You can think, meanwhile, what does it affect exactly? But we'll see now what huge change it makes on a profile. This is the profile of it, taken with a profiler that produces only Python stacks. Well, we can clearly see that all time is spent inside subprocess run. Well, that's the only thing that this function is doing. The snippet is doing. It's just calling subprocess run. But where? This profile tells us nothing. We can't work with that to actually optimize the code and understand where is my CPU that I'm going to. If we take this profile again, this time with a profiler that produces also native stacks and kernel stacks, in this case, this is our eBPF-based profiler for Python. We now see 2 new stacks, kernel stacks. It might be intimidating at first. When I first saw it, I also didn't know any names of the kernel stacks that I'm seeing here. But once I looked up, copy page range and unmap page range, the 2 functions at the bottom of the stacks, I was somewhat able to understand the issue. What's happening here, basically, a quick technical dive, is that subprocess run, in order to start a new process, it has to fork and exec on a Linux system. Forking and executing requires copying some information from the previous process, and the more memory that our process has, we now have to copy more metadata about its memory. It's internal to the memory managing in Linux. It's basically, it has to copy many, many parts of the page tables, and the more memory I have, the more I have to copy, and that costs time. Now, searching for those 2 functions online, I did find some possible solutions for the problem. One of them actually had an open issue in Python's bug tracker, which was stale. So I bumped it, and it got merged for Python 3.10. And now running this same application with Python 3.10 shows a very different profile. This is actually something that I had encountered in my previous workplace. Our CI was written in Escons, and it was taking 8 cores for 1 hour, and 50% of the profile was forking and executing, which is awful. So for that, I had to find it out and get it fixed in Python 3.10. Now, what I like about this sample is that it shows you one of the most beautiful things about profiling. You don't have to be the master of a code base in order to profile it. I've never seen those kernel functions before. I wasn't acquainted with this area in the kernel. And yet, just by seeing those names and Googling a bit, I was able to figure out what the problem is and figure out multiple possible solutions and get one implemented to speed up our CI, which is very cool. Another example. Has any of you seen this message with pip? It's quite new. Well, the other day I upgraded my pip to the release from last month, from March. And I tried to install one of our local sub-projects, and pip was taking much longer than usual. It also kept printing me, I'm taking much longer than usual. You might need to stop me, but it just kept printing that, and I needed that project installed. So I run top, and I see that pip is indeed taking 100% CPU. And as a performance guy, what do you do at this point? You profile it. You profile it. Now, this profile is much more complex than what we've seen before. It's also a very short profile. Now, contrary to what I've said before about continuously profiling, if you understand what a program is doing, understand that it's doing exactly one thing now, then you can profile it for even 10 seconds and get a good image of its behavior. If you're not sure about what the program is doing, then you should profile continuously and wait for hours or days before working with the data. Anyway, this profile is indeed much more complex than what we've seen before, and by looking at it, I could not pinpoint where should I focus to improve the performance. So we'll now see some tools that can help us. One thing with profiling and optimizing is that you work for the major issues. You leave the tails behind and you focus on the big problems because there are many, many problems to fix, but only some are actually relevant for the overall behavior of your code performance-wise. So we can apply the same thing on the profile. Instead of viewing all frames, which is, thousands of them, I don't know, we can apply a weight filter and see just, let's say, the top percentile of them. And it takes this profile and converts it to this one, which is much more simpler to read and comprehend. And looking here, we can see that there roughly are 4 or 5 different call stacks, which probably correspond to 4 or 5 different major tasks. And now we can look into them individually and decide where we want to dive and optimize. Another example is a table view. It is often said that, said by Brendan, which is, by the way, the creator of flamegraphs, Brendan Gregg. I put some reference to his site later. He said that he created flamegraphs because profiles were generating walls of text, and it was hard to read them. Now, he was not wrong. This is a short profile I took on my machine, and the raw textual representation of it is 500,000 text lines. It's not readable. Flamegraphs help you make it readable and readable by humans. However, there are other ways to display graphs, to display profiling data textually that can be useful. A table view breaks the graph and shows functions with some attributes and fields and lets you sort or order them appropriately. Now, the important thing is that we're not looking at call stacks, we're looking at functions. And let's see how it can be used. Let's take this example of a simple flame graph. We have the A function calling into B, and we also have A calling into D and C, which then call into B. We can view functions by the number of occurrences they have in a graph. The more occurrences a function has, the more unique sites it is called into. For example, B has 3 occurrences, and D has exactly 1. Why does it matter? Because if a function has, let's say, 100 occurrences, then trying to optimize the way the function is used, for example, changing its arguments or parameters, requires much more effort because we have to fix many, many, many sites. If a function has, for example, like this function from pip's profile, the constructor of the version class, it has 29 occurrences. So fixing 29 code sites is lots of work. In this case, it's better to optimize the function itself if we are trying to optimize its execution time. On the other end, a function like D, which is called exactly once, we can choose to optimize the call site and not optimize the function itself. For example, cache the result of the function and avoid from calling into it completely. It helps you decide where to focus. Another important trait, or 2 traits, are total time and own time. given a function, the total time of it in a flame graph is the number of samples or the percentage of samples that included a function and functions called by it. When we have a function with I total time, we can try to avoid from calling into it, like caching its result or changing the way it is invoked. On time, on the other hand, is the time that this function was executing on the CPU itself. A function with high on time can be optimized, like just its code should be optimized, because it itself is a bottleneck. So in this case, A is a total time of 100% because the entire profile includes A, and B has total time of 30%, and that should be the function we focus. In a table view, we can view functions ordered by total time and on time. For example, again, in pip's profile, the version constructor has on time of 20%, which is very, very, very high. And if I were to optimize this pip, I'd start with that function, the most intriguing one in the profile. OK, I think I'll skip that because I want to show you a demo. We'll skip this one. OK. It was a lot of information. I don't expect you to remember anything. I do expect you to remember at least one or two ideas, because these are very useful and they will help you profile should you try and enter this field. Now, let's get some practice. This is what I like to call the profiling circle. We continuously profile our applications. We analyze the results and pinpoint the interesting call stacks functions. We implement fixes and improvements for those functions. We deploy the fixes. We verify the results in the new profiles. And we repeat. That's the life of the performance engineer, let's say. All right, I have a demo, and I think we'll do it live, if things like me. Yeah, OK. So, yes. This is a simple Flask, and the font is all right? Yeah. Simple Flask and a SQL Alchemy demo. I don't know SQL Alchemy. I just wanted something simple, so maybe the code is stupid, but I just did what every developer does. I went to Google, found the first answer on Stack Overflow, and copied the code. So that's what real developers use, I assume. I took a simple SQLite database that includes information about artists and shows. And I have a Flask application that exposes an endpoint that you can send the artist name, and it tells you true or false if it exists in the database. Very simple. The major code piece here is, no, the interesting function is this one. It gets the name, and it returns you the result from the database. Now, let's go to the profiling result. Not this one, this one. Yeah. So this is the profile page from some AWS server that I ran the application on. We can focus on the GUnicorn, and we can actually focus on the container itself. It's fairly complex. Most of the code here is actually of Gunicorn itself, which is also interesting to look at, but today we will focus just this one function of SQL Alchemy. So it was called does artist exist. We can see that it takes 34% of the profile. We can focus on that. And we're saying that it splits to roughly 4 or 5. Can maybe make it a bit, I don't know how to enlarge it. Splits to maybe 4 or 5 different stacks. This major one here is the actual query, the actual communication with the SQLite database. The other two, for example, this one, is the exists function call that we saw before. This one is the equal operator from this part. Now, when I saw this profile, I thought, why would it take time? I mean, this part doesn't really change. The only thing that changes in this expression is the name. Why should it actually, why do I need it to execute every time and consume CPU resources for my server? So I did a small modification to the code. Without knowing SQL Alchemy, it might be completely wrong and not the right way to do it, but it worked. A simple cache, a cache on the name that returns this expression and just saves it for each name instead of regenerating it every time. I actually wanted to show you it running. Here I have let's start with the bad version. Traffic generator and Docker stats. The bad version is stable at about 51, 55%. I can also run the profiler, but to show how easy it is. But we will not wait for the profile data to arrive because that will take a few minutes. Basically, just running a simple Docker container on the machine, and it is what produces this entire profile of my system. That includes all parts. This is just the container. All right. So that is the fixed version. And now let's see how the fixed profile looks like. As I said, after deploying a fix, we always verify the profile. So we can take the good one, focus on the good container, and search for the function does RDS. Okay, first of all, now I can see that it takes 28% and not 34%, which is a good indication that I've reduced its used CPU time. And looking into the particular stack, we can also see that only the query part remained, and one small thing here. And the exists and equal operator are completely gone, which means that our cache works just as we have expected, which is good. We can also run the updated version of it. Stop the profiler, stop traffic, stop the app, and I'll show you that it actually consumes less CPU now. Because again, only viewing it in the profile is not enough. What we want to improve is not the flame graph or profile. We want to improve the resource consumption because that's what we're paying for. But I will show you that the fixed application has lower CPU utilization, as you can see here. It mostly doesn't cross the 50%. So that's just, again, a simple dump example. I don't know SQL Alchemy, but it shows you roughly how it works like, how this circle works like. You run a profiler, you find something that looks bad, you try to fix the code, you run the profiler again, it looks better, you're happy, and you continue to do that forever. That's it. Okay, back to the presentation. That's what we've skipped. 2 minutes, I'll handle it. I have one small fun example where I've used gprofiler on our systems that I wanted to show. This is a profile of one of our big Python applications. I've marked in blue a function called remove handler ref, which I saw taking 3% of the profile. 3% is not enough, but as I said, profiling is done iteratively. You find one thing, fix it, find another thing, fix it, and eventually those things add up. 3% was too much for me, so I decided to look into it. It's a function from Python's standard library, and it looks like this, and it really does nothing. It takes some lock, checks if an object is in a list, removes it from the list, releases the lock, nothing. Well, the performance costly thing here is that it looks through the list twice. And in our application case, the list was about 40,000 or 50,000 items. So this lookup was actually taking the majority of the time. So I sent a simple pull request to CPython and switched it to use exception-based handling of the missing item in case it doesn't exist. So if you're using logging, I help to make your code a tad bit faster. But in our case, it was very significant. It was about 1 or 2% of our big application, which is a lot. So it's cool. OK. I hope you've enjoyed and learned a few new things. I have some takeaways. One of the big things that I want you to take from here are these. One, always start by profiling. optimizing without profiling is bad, and you're not making the right choices. I'm not from the performance world. I used to prematurely optimize, and in hindsight, I can tell that I was making the wrong choices. And now I profile everything in my life. Another thing is, don't be afraid of diving into code bases that you do not understand. Oftentimes, the performance heavy part is not from your code or code in your organization that was not written by you, or third library code or kernel code or whatever code. Don't be afraid and look into it. Profiling leads you to the key. You do not need to master a code base in order to profile it. And one last thing, always profile production and always profile continuously. That's it. Thank you. You can try free profiling, and I've put some more interesting resources below. And we're out of time, but if you have any questions, then I'm happy to take them. Right. Yeah.
Just a question about when you're using some code which has a lot of concurrency in it, does it work well? I mean, typically you have some logs being leveraged. Does it show into the flame graphs?
So logs, time spent waiting for logs is not shown in flame graphs because the application is asleep and waiting in the kernel for the lock or resource to be released. Whether it's a lock, waiting on a socket for data to arrive, waiting on a blocking file read, that is not shown. What is shown is if you're continuously releasing and acquiring a lock, it has some CPU cost in some cases, and that will be shown in a profile. But in order to profile bad networking, bad locking, bad file usage, you have another types of profiles. Flame graphs can also be used for this type of profiling. It's called, big word, off-CPU profiling. You can read about it online, but generally the answer for this type of profiling, the answer is no. You will not see this data in your profiles. Okay, thank you.